Hello everyone, it's my pleasure to talk about our recent work on private graphon estimation via sum of squares. This is joint work with Hongjie Chen, Yiding Hua, Tommaso Diossi, Chihong Liu, and David Stoyer. The talk will be about polynomial time algorithms for random graph estimation with no differential privacy. The key techniques involved in this paper will be a new robust low-rank estimation algorithm from semi-definite programming, particularly sum of squares hierarchy. And we also use the sum of squares exponential mechanism developed in recent years. Many real-life networks can be captured by random graph models. Random graph estimation, therefore, is a central topic in the theory of graph data analysis. A natural and fundamental question in random graph estimation is whether we can estimate the underlying distribution generating the random graph. For this, we need a model for the graph generation process. Graphon is a powerful model for capturing many random graph distributions. Given a symmetric function mapping from 0, 1 squared to positive real values, a random graph can be generated in the following way. In the first step, we assign each of the n vertices a random value uniformly sampled from 0 and 1 independently. In the second step, we connect each pair of vertices independently with probability given by Wxi xj, where xi xj are the real value assigned to the vertices I and j. Many real-life networks are actually sparse. For better modeling such graphs, people also study sparse graphons. Given the target density rho, each pair of vertices is independently connected with probability rho times w, such that the expected edge density is given by rho. A very important special class of a graphon is a block graphon. In such case, the graphon function is a blockwise constant. And as a result, the edge connection probability matrix is a block matrix. For the simplest case, for two block graphons, we divide the 0-1 interval into two equal-sized intervals. And then we get 4 blocks. Because the function is symmetric, we can assign at most 3 different values to this function. Why people are interested in block graphons? Because with increasing number of blocks, we can approximate the general graphon with a smaller and smaller approximation error. Given the random graph generated from the graphon, a natural task is to estimate the underlying graphon generating the graph. A natural error metric is the L2 distance between two functions. However, because under permutation, different graphon functions can lead to the same distribution of the random graph, we cannot hope for meaningful guarantees under the L2 distance. As a result, we need to consider the minima taken over bijective mappings, aligning the two graphon functions. In the setting of block graphons, we can define the distance between two k by k matrices based on the delta 2 distance between the graphon functions generated from these k by k matrices. Equivalently, such distance can be defined as Froebel's distance between two k by k matrices aligned by doubly stochastic matrices. So a natural question in the learning theory of graphon is what is the optimal rate for learning the underlying graphon function? In the case of a k-block graphon, the optimal estimator is given by the maximum likelihood estimator. So given the generated random graph, the maximum likelihood estimator gives error guarantee log k over rho n. On the other hand, for polynomial time algorithms, we have error guarantee k over rho n based on singular value decomposition. So we can see that there is a potential information computation gap k versus log k. In this paper, we are interested in estimating the underlying graphon without differential privacy. Differential privacy is a notion in security motivated by protecting user privacy against differential attacks. So in this scenario, the adversary can try to detect whether a user element is in the dataset by comparing the outcome of the algorithm in neighboring datasets, which differ in exactly one data point. Differential privacy requires that for the algorithm, it gives similar outcome on arbitrary neighboring datasets. Formally, for n neighboring datasets, the algorithm outputs should be close to each other in the sense that for n set S, the probability that the algorithm outcome falls in the set S is close to each other within a factor of e to the power of epsilon. When it comes to graph data analysis, a question is what is the correct notion of a neighboring dataset? There are two typical notions of differential privacy in graphs. The first one is no differential privacy, where for neighboring datasets, the graphs differ in one node. For the other notion of differential privacy, for neighboring datasets, the graphs differ in one edge. One can easily see that no differential privacy is stronger. And I would argue that it's also a more natural notion because we want to protect the privacy of a user in general. Previous exponential time private algorithm developed in 2018 is based on the maximum likelihood estimator and exponential mechanism. They can output a k by k epsilon node private matrix such that for the associated k-block graphon, the distance from it to the underlying graphon is bounded by log k over rho n plus k squared log n over n epsilon. So the cost of privacy is bounded by k squared log n over n epsilon. The key question that we try to answer in this paper is whether we can learn the graphon efficiently in polynomial time and node privately with a similar privacy error bound. For our result, we obtain an algorithm which runs in time n to the power of poly k, giving epsilon node private matrix, generating a graphon function which achieves error rate k over rho n plus k squared log n over n epsilon. We also give information theoretical level bound, showing that the error term k squared log n over n epsilon might be inherent. When k is a constant, our algorithm runs in polynomial time. One conceptual message here is that for constant k, epsilon, and sparse graphs, the privacy error term is negligible compared to the non-private error term. So we get privacy essentially for free. In this paper, we mainly rely on the classical exponential mechanism. Given the adjacency matrix, we design the score function for each k by k real symmetric matrix B with sensitivity delta. The sensitivity of the score function is defined as the upper bound on the difference of the score for arbitrary neighboring datasets. Then, in exponential mechanism, we sample from the exponential distribution with exponent given by epsilon times the score function over 2 times delta. It's automatically guaranteed that the sampled estimator will be epsilon differentially private. For the utility analysis, one can show that with high probability, the deviation of the score value of the sampled matrix B from the maxima will be upper bounded by the dimension of B times the sensitivity times log n over epsilon. For the ideal score function, we can see that to get good utility, to obtain ideal recovery guarantees, you expect 3 good properties from the score function. First, we want to show that if the score function is large, then it implies that the sampled matrix B is close to the underlying k by k matrix B0. Second, we want delta to be small, which is to say, we want the score function to have a small sensitivity. Third, for computational complexity, we want the score function to be tractable. A naive strategy for designing the score function is by plugging in the non-private estimator computed by running singular value decomposition on the adjacency matrix A. However, such algorithm cannot give us some meaningful utility guarantees. This is because the algorithm based on singular value decomposition is not robust. This leads to the high sensitivity of the score function, and thus gives us much worse utility bound. Instead, we designed the score function using sum of squares hierarchy. The based on the framework of sum of squares exponential mechanism developed in a recent work. The advantage is that the score function can then be computed in polynomial time, and it enjoys small sensitivity and thus gives us a good utility bound. So what is sum of squares hierarchy? Many non-convex optimization problems can be formulated as polynomial optimization problems. Given a set of polynomial constraints, we want to show identifiability proof that any program variable satisfying these constraints must be close to the parameter x0. Under the sum of squares framework, we want to certify this inequality with a sum of squares of polynomials. On a high level, if we have a simple proof captured by sum of squares, for example, Cauchy-Schwarz or Hurley inequality, then the guarantees of the identifiability proof will automatically hold for a convex relaxation of the polynomial system. Especially if we have a degree D sum of squares proof, which means that the degree of polynomial on the right-hand side of the equality is at most D, then we can instead consider a semi-definite programming with size n to the power of D. The program variable in this semi-definite programming is called a pseudo distribution, which in some sense is similar to the distribution over the program variables. We use a sum of squares hierarchy to design the score function for the privacy mechanism. We assume that the n vertices are equipartitioned into k communities for simplicity. In this case, we can parameterize a model by a balanced community membership matrix with size m times k. It then enjoys a number of elegant properties used for the later identifiability proof. Inspired by the previous maximal likelihood estimator, we designed the score function by considering its sum of squares relaxation. One can show, as in the previous literature, that such a score function has sensitivity bounded by big O n. Now we can set the sensitivity delta in the exponential mechanism to a big O n. Exponential mechanism promises us that the sampled estimator will be epsilon differentially private. Moreover, with high probability for the sampled matrix B, its deviation from the maxima will be upper bounded by the dimension of B times the sensitivity bound times log n over epsilon. We know that the dimension of B is at most k squared, and the sensitivity is upper bounded by big O n. Now we show the lemma that if the score function is not far away from the maxima, then this implies the small delta 2 distance between matrix B and matrix B0. By plugging in the eta from the exponential mechanism, which is to say k squared and log n over epsilon, we have the ideal delta distance bound on B and B0. For sketching the proof of the lemma, we consider the case where eta is 0. In this case, we first give sum of squares identifiability proof for the n by n edge connection probability matrix. We mimic the proof for previous singular value decomposition algorithm. Particularly, we show that the arrow is upper bounded by the inner product between a rank 2K matrix and a spectrally bounded matrix. Next, for any matrix B, we show that if there is a degree L pseudo-distribution over the community membership matrix, such that the estimation error of the n by n edge connection probability matrix is small, then when the level is high enough, this implies the small delta 2 distance between B and B0. The key observation here is that Z transpose Z0 is a doubly stochastic matrix up to scaling. If there is a degree L pseudo-distribution over the community membership matrix, such that the estimation error of the edge connection probability matrix is small, then this implies a pseudo-distribution over doubly stochastic matrices aligning the matrix B and B0. When the degree L is high enough, we can use the argument from global correlation rounding to show that there exists a doubly stochastic matrix aligning matrix B and B0. The existence is enough for bounding the delta 2 distance between matrix B and matrix B0. We extend our result to sparse graphs. If we only consider graphs with a bounded degree, we can have a better sensitivity bound. Therefore, one could hope for better guarantees in sparse graphs. However, one issue is that we need to bound the sensitivity for all graphs instead of just the typical graphs sampled from sparse random models. In the previous paper, people show a very general and powerful Lipschitz extension lemma for obtaining exponential time algorithms in sparse graphs. In our setting, we borrow their idea, particularly considering the stand score function as in the dense graph case. It has small sensitivity on the degree bounded graphs. Then one could construct an extension of the score function to all graphs under the framework of sum of squares hierarchy. This gives us a computational efficiency. By combining the extended score function and the exponential mechanism, we get private algorithm with ideal utility bound in sparse graphs. In conclusion, we obtain a polynomial time algorithm for no differentially private graphon estimation when k is a constant. The rate of our algorithm matches the information theoretical threshold up to a computation statistical gap. There are a number of interesting open questions which we leave for future work.